Today we're going to look in section 4.4. If you remember in previous sections in chapter 4, we would find the zeros of a polynomial by factoring. For example, given this polynomial, f of x is equal to x cubed minus 2x squared minus 9x plus 18. If we were told to find the zeros by factoring, what we would do is take the greatest common factor out of the two terms. Since it has four terms, we're going to factor by grouping. So out of this 2 right here, note the greatest common factor is x squared. And out of these 2 right here, the greatest common factor would be a negative 9, because you want to take a negative out. So that would factor as x squared times x minus 2. And if we take out a negative 9 here, you have negative 9 times x minus 2. Then notice both of these expressions, x squared and negative 9, are being multiplied by this x minus 2. So that's the greatest common factor. That will come out as x minus 2, and then what you have left is x squared minus 9. Notice this polynomial is not completely factored because this x squared minus 9 will factor again. Since it is a difference of squares, it will factor as x plus 3 times x minus 3. So we have factored that polynomial function to be x minus 2, x plus 3, and x minus 3. Now to find the zeros, we would set each factor equal to 0 and solve for x. So we would get x equals 2, x equals negative 3, and x equals positive 3. So the polynomial function x cubed minus 2x squared minus 9x plus 18 has zeros of 2, negative 3, and 3. Well, in section 4.4, we're going to go backwards. You're going to be given the zeros, and you're going to have to come up with the polynomial. So with that in mind, I'm going to look at number 5 on page 342 in your book. And it says, find a polynomial function of degree 3 with the given numbers as zeros. And number 5 uses the square root of 2, negative square root of 2, and 3. So again, you're going backwards. Instead of being given the polynomial function and factoring to get x, this time you're given the x's or the zeros, and we want to go backwards. So these are your 3 zeros. So that means you got to come up with the factors. Well, just like up here, the x minus 2 gave us a positive 2 as a 0. To get the factor for x, to get the factor for the square root of 2, it must have been x minus the square root of 2. To get the 0 negative square root of 2, the factor must have been x plus the square root of 2. To get the factor of, or to get the 0 of 3, it must have factored as x minus 3. Okay? Because see, you're going to have to add the opposite. See over here, this factor was negative 3, but to get solved for x, we added 3 to both sides. So the same thing here. You got it's like the opposite in the factor. So now this is how this polynomial is going to factor. So if I label this f of x, these are the given zeros. So then I've come up, these must be the factors. But now what's the polynomial? Well, to get the polynomial, we're going to have to multiply this out to get the polynomial. So how in the world are we going to multiply all 3 of these polynomials together? Well, the first thing you should do is FOIL the first 2. Or maybe you realize that that's a special product, and what makes it a special product is that the first terms are the same, the last terms are the same, and the signs are different. So that will multiply out to be the first term squared minus the last term squared. So that would be x squared minus the square root of 2 squared for this right here, and then just bring down the x minus 3. Just bring it on down, okay? So how in the world does this simplify? Well, that's going to become x squared minus 2, because when you square a radical or you square a square root, they undo itself. Then you still have the x minus 3. So then how are you going to finish multiplying this out? I would FOIL it. And remember what FOIL stands for. First, outer, inner, last. So you'll do first times first. First times first. And then you'll do outer times outer. Then you'll do inner times inner. And last times last. So that first times first is x squared times x, which is x cubed. And then outer times outer, which would be negative 3 times x squared, which would be negative 3x squared. And then the inner times inner is negative 2 times x, or negative 2x. And then your last times last is negative 2 times negative 3, or positive 6. So that means the polynomial function where the given zeros are square root of 2, negative square root of 2, and 3, the polynomial function that gives you those 3 zeros is x cubed minus 3x squared minus 2x plus 6. And that's number 5. Now the key thing to remember when you're doing these is that you could have a 0 left out but still get it. If you'll remember from the complex numbers, remember complex numbers, or let's say complex zeros, are in conjugate pairs. If 1 plus 3i was a 0, then 1 minus 3i is also a 0. Same thing if negative 5i was a 0, then so is positive 5i. Okay? So that is also true of radical zeros. If negative square root of 3 is a 0, then positive square root of 3 is also a 0. If 2 plus the square root of 7 is a 0, then 2 minus the square root of 7 is also a 0. So that will come in handy to get more polynomials. So if we're looking again on page 343, let's look at number 26. Number 26 says, suppose that a polynomial function of degree 5 with rational coefficients has the given numbers as zeros. Find the other zeros. So in number 26, you were given the zeros of 3/4, negative square root of 3, and 2i. So it said, suppose that a polynomial function of degree 5, So you're given 3 zeros. So if it's degree 5, that means it's got 5 zeros. So you need to find 2 more. So what are the other zeros? Well, remember that your radicals and your complex are in conjugate pairs. So the other zeros are positive square root of 3 and negative 2i. Okay, so on the same page, let's look at number 29. On number 29, you were given 6, -3 plus 4i, and 4 minus the square root of 5. Same instructions, which said there's a polynomial of degree 5, and you're given these 3 zeros. So what are the other zeros? Well, the other zeros, remember, here you have a complex number, and here you have a radical number. So they're in conjugate pairs. So -3 plus 4i is a 0. That means -3 minus 4i is also a 0. And so is 4 plus the square root of 5. And remember, conjugates aren't completely opposites. That 4 is going to remain positive, only these signs change. They're in the middle. So sometimes you will have to use that fact to find the polynomial function. For example, if we're given number 38, the instructions say find a polynomial function of lowest degree with rational coefficients that has the given numbers as sum of its zeros. So in number 38, you're given 3 and -i. That's what you're given. So what's the other zeros? Well, since you're given -i, then you know another 0 is positive I. Why? Because the complex zeros are in conjugate pairs. So now I've got 3 zeros. So how in the world does this thing factor, or how did it factor? Well, it must have factored. To get 3, it must have been x minus 3. To get -i, it must have been x plus I. And to get positive I, it must have been x minus I. Now we're not done yet because this is in factored form and we need to know what the polynomial function is. So we need to multiply this out. Since these two are the most alike, let's multiply these out first. And if you notice, that is a special product because the first and the last terms are the same and they only differ by a sign. So I'm going to leave the x minus 3 in front, and this will factor as the first term squared minus the last term squared. Okay, so you've got x minus 3 and then x squared minus, well, what in the world is I squared? Remember, I squared is -1, so if I replace that with -1, the two minuses here become a positive. Okay, so you've got x minus 3 times x squared plus 1. Again, this is a binomial times a binomial. So in order to multiply that out, we need to FOIL it. So if we do first times first, x times x squared, give me x cubed. Then if I do, I'm going to go ahead and do the inner first. -3 times x squared is -3x squared. X times 1 is x, and then last times last, -3 times 1 is -3. So there's your polynomial function that you were given a 0 of 3 and -i, but because the complex come in pairs, we know that another 0 is positive I, so we had to write that in as a factor. And we multiplied it all out, and we got x cubed minus 3x squared plus x minus 3. Sometimes you will be given a 0 and expected to find the other zeros. I'm looking at number 43, again on page 343. And it says, given that the polynomial function has the given 0, find the other zeros. Well, your polynomial function is f of x equals x cubed plus 5x squared minus 2x minus 10, little semicolon, and a -5. So that means -5 is a 0. Because this is third degree, there's 3 zeros, and we're given 1. So how do we find the other two? Well, you're going to have to use synthetic division to get the depressed equation. Because if you'll remember your depressed equation, if it starts off as x to the third, your depressed equation will become x squared. So remember how to do that. This number will go on the outside on the shelf. And then you'll write your coefficients to the right, 1, positive 5, negative 2, negative 10. Skip a line and draw a line. Your first number will come straight down. Then negative 5 times 1 is negative 5. And if you add that straight down, you'll get 0. And you multiply vertically, or multiply horizontally. Negative 5 times 0 is 0. Then you add straight down. Negative 2 times negative 2 plus 0 is negative 2. Negative 5 times negative 2 is positive 10. And notice when you add that straight down, you get 0. You're supposed to get 0 because a negative 5 is a 0. So if you don't get 0 here, you've done something wrong. Now from this result here, this line right here, we get what's called, again, what's called the depressed equation. Because this started off as x to the third, the depressed equation will be x squared. So that's x squared, there's no x, minus 2 equals 0. And I'm going to set that equal to 0 because this means that f of x, the negative 5 was 1, 0. So to find the other zeros, you set it equal to 0 and solve it. Notice this will not factor. So how can we solve for 0? Well, how about let's add 2 to the other side and get x squared equals 2. And then to solve for x, you'll remember to take the square root of both sides. And when you take the square root of both sides, you get two answers, a plus and a minus. So x is equal to plus or minus 2. Now the instructions for number 43 says, find the other zeros. So given that negative 5 was a 0, the other zeros are positive square root of 2 and negative square root of 2. And this one has 3 zeros. You're given 1, and you found the other 2. Sometimes it is necessary to have a starting point if you're not given the zeros. I am looking at number 50, again on page 343. And this is given f of x is equal to x to the 7th plus 37x to the 5th minus 6x squared plus 12. On page 338 in your book, you have the rational zeros theorem. Okay, it says you've got this big, long, ugly polynomial where all the coefficients are integers. Okay, it says consider a rational number denoted by p over q, where p and q are relatively prime. Okay, and common factors are, if p over q is a 0 of p of x, then p is a factor of a sub naught, and q is a factor of a sub n. What all that means is that your possible rational zeros can be found by dividing factors of the constant by factors of the leading coefficient. That's where that p over q comes in. That's what that means. So back to number 50 from page 343. It says list all the possible rational zeros. So you want to make a list of all the possible rational zeros. So the possible rational zeros will be factors of the constant divided by factors of the leading coefficient. So for our particular problem in number 50, our constant is 12, and our leading coefficient is 1. Here's our constant. And our leading coefficient is understood to be 1 because it's the coefficient of the one with the highest degree. So factors of 12. Factors of 12. 1 times 12 and 2 times 6 and 3 times 4. So you've got 1 times 12, 2 times 6, and 3 times 4. And it's always going to be plus or minus because you can have positive 3 times positive 4 is 12, and negative 3 times negative 4 is 12. So it's always the plus or minus divided by factors of the leading coefficient. Well, the only factors of 1 are plus or minus 1. So your possible rational zeros would be all of these numbers on top divided by each number on the bottom, which in this case it was fairly simple because you only had one factor in the bottom. So the possible rational zeros, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Now sometimes this can get pretty confusing when the leading coefficient is not 1, such as number 53. Number 53 is f of x equals 15x to the 6th plus 47x squared plus 2. So notice this time your constant is 2 and your leading coefficient is now 15. So to make a list of your possible rational zeros, these are all the numbers that could be a zero of the polynomial. You want to take the factors of the constant. So you want factors of 2, which would be 1 times 2, plus or minus 1 times plus or minus 2, divided by factors of the leading coefficient. Now the leading coefficient is 15. So factors of the leading coefficient of 15, that's a pretty big, well, there's more of those. So you've got 1 times 15, and you've got 3 times 5. And I just wrote them in order from smallest to largest. It just makes it easier to read. So this time, notice you've got more factors in the denominator than you do the numerator. Up here, you only had one factor in the denominator because factors of 1 is 1. All right, so here, to find all the possible rational zeros, you will have to divide each numerator by each one of these denominators. Okay? So your possible rational zeros are, let's just take them one at a time. These two on top divided by this one on the bottom. So that'd be plus or minus 1 and plus or minus 2. Then take the 1 and the 2 on the top and divide it by plus or minus 3. So that'd be plus or minus 1/3 and plus or minus 2/3. And then do plus or minus 1 and plus or minus 2 divided by the 5. So that'd be plus or minus 1/5 and plus or minus 2/5. And then those two on the top divided by 15. So that'd be plus or minus 1/15 and plus or minus 2/15. Sorry, that got scrunched up there. But those are all your possible rational zeros. 1, 2, 3, 4, 5, 6, 7, 8. So there's 16 of them because it could be the positive ones or the negative ones. The very first example we did today was f of x equals x cubed minus 2x squared minus 9x plus 18. And we factored it by grouping, and we got the zeros were 2, -3, and +3. That was the very first problem we did today. Well, let's look at the possible rational zeros. According to the rational root theorem, the possible rational zeros are going to be factors of 18 divided by factors of 1. So that would be factors of 18. Well, you can have 1 and 18, 2 and 9, 3 and 6, and I do believe that's it. All divided by factors of the leading coefficient, which is 1. So all of these divided by 1 is the possible rational zeros, which just happens to be the numerator or this list on top. So the possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18. Well, when we worked this problem, we solved it by factoring. We got the zeros to be 2, -3, and 3. Well, look, they're in the list. Here's +2, here's -3, and here's +3. They're all in the list. See how that works? Let's suppose we're given a polynomial function and we want to find the zeros, and we weren't giving any starting points. Nothing to start with. All right, let's suppose we were given polynomial function f of x equals x cubed minus 2x squared minus 3x plus 6. And what we want to do is to find the zeros and then write the polynomial in factored form. Well, in this entire section, we were given the zeros and asked to go backwards, but here we're not given anything. Okay, so let's use the calculator. So we're going to use the calculator to get a zero or a starting point. So how in the world are you going to use the calculator? Glad you asked. Well, take your handy dandy calculator. Okay, we're going to go to y equals, and we're going to type in your y equals this polynomial. So we're going to type in x to the third minus 2x squared minus 3x plus 6. By the way, do you know the end behavior of this polynomial? It goes down to the left and up to the right because degree is odd, so it's opposite directions. Sorry about that glare there. Let's see if I can fix it. So because it's odd degree, their ends are in opposite directions. Because the leading coefficient is positive, it will go down to the left, up to the right. But what is the y-intercept? Well, the y-intercept, if you let x be 0, all of these cancel, and you're left with 6. Okay, so that's a review from the other day. All right, so now let's go back to finding the zeros of this big ugly polynomial. So we're going to put that in our calculator. Okay, to get a starting point, put this in the calculator and go to second table. All right, so what we're looking for is a 0 in the y column. So use your arrows to go up and down until you see a 0 in the Y column. Not in the X column, but in the Y column. Oh, right there's one. You see that? When X is 2, Y is 0, right there. Okay, so that means X equals 2 is a 0 from the calculator. X equals 2 is a 0. Great, we've got 1. Would 2 be in the possible rational list? Sure would. Your possible rational zeros would be factors of 6 divided by factors of 1. Well, your factors of 6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Sure enough, there's the 2. So since 2 is a 0, well then how do we find the other 2 zeros? And you know it's got two more zeros because the degree is 3. So what you want to do is use synthetic division to get the depressed equation. So 2 goes on the outside. And you'll use your coefficients. 1, -2, -3, +6. So you'll skip a line and draw a line. Remember when you do synthetic division, the first number comes straight down. So bring your 1 straight down. And then let's multiply diagonally. 2 times 1 is 2. Add vertically. -2 and 2 is 0. Multiply diagonally. 2 times 0 is 0. Add vertically. -3 and 0 is -3. 2 times -3 is -6. Add, and you get 0. If we didn't get 0, we did something wrong because 2 is a 0, so your remainder should be 0. Now let's look at this depressed equation. Well, if your equation started off as x to the third, the depressed equation will be x squared. So your depressed equation is x squared, there's not an x, minus 3. If we set that thing equal to 0, we can solve for x like we did on the other one. So if we solve this for x, notice that won't factor because it's not a difference of squares. It's a difference, but it's not a difference of squares. So what you would do is add 3 to both sides, and you get x squared equals 3. And then to solve for x, you would need to take the square root of both sides. And remember, when you take the square root of both sides, you get 2 answers, a plus and a minus. So x is equal to plus or minus the square root of 3. So for this big ugly polynomial up here, our zeros are, we got 2 from the handy dandy calculator, and then we use the synthetic division to get a depressed equation, which we then solved to get positive square root of 3 and negative square root of 3. So we found the zeros. We found the zeros. They're 2 and 3 and negative square root of 3. But then we need to write f of x factored. Well, how in the world can you write it factored? Well, just like we did earlier, go backwards. So your polynomial, if 2 is a 0, then that factor must have been x minus 2. If square root of 3 is a 0, then that factor must be x minus the square root of 3. If negative square root of 3 is a 0, then that factor must be x plus the square root of 3. Dun-da-da! Now it's factored, and there's your zeros. The next thing we're going to look at in section 4.4 is Descartes' rule of signs. It's on page 341, the big brown box. Okay? It says a lot of stuff, but you have a polynomial p of x written in descending or ascending order. Now it must be written like that. Can't be jumbled up. It's got to be in ascending or descending order. And then what you're going to do is count the sign changes. Okay? That's what all this stuff means. The number of positive real zeros will be the number of sign changes, or that number decreased by an even integer. And the number of negative real zeros will be the number of sign changes in P of negative x, or that number decreased by 0. Okay, so we're going to look at that. It's kind of neat how this works, and if we had a lot of time, we could put all this together with the rational root theorem, Descartes' rule of signs, and you can see all the possibilities of where all the zeros come from. But due to lack of time and the handy-dandy work of the calculator, I'm just going to hit the high points. So using Descartes' rule of signs, to give the number of positive and negative real zeros. Okay, so the example I have for you is horrible negative x to the 8th plus 6x to the 5th minus x to the 3rd plus 2x minus 2. Now notice how it's written in descending order. All the powers go down, 8, 5, 3, 1, none. So it's already in descending order. So to use Descartes' rule of signs, note the number of sign changes in the given function. In our case, it's h of x. So I'm going to rewrite it down here so I can mark on it a little bit. Okay, so let's look. Notice from term to term, this thing has 5 terms, okay? From the first to the second term, it went negative, positive. So that's one sign change. And then from the second term to the third term, it also changed signs from positive to negative. So that's one other sign change. From the third to the fourth, it went negative, positive. That's one more sign change. And then from the fourth term to the fifth term, it went positive to negative. Another sign change. So in h of x, there were 4 sign changes from term to term. Now, what in the world does that mean? Well, this is what it means. That means there are 4 or 2 or 0 possible positive real zeros. Okay? Now, notice what I said, 4 or 2 or 0. So what you have to do is subtract an even number until you get down to 0 or 1. So that means there's 4, or 4 minus 2 is 2, or 2 minus 2 is 0. Of positive real zeros. You're just denoting the sign change and subtracting 2 until you get it down to 0 or 1. All right? Now that's the number of positives. So to determine the number of negative sign changes, we have to look at h of negative x. Note the number of sign changes in h of negative x. So how in the world are we going to find h of negative x? Well, you just substitute in a negative x for every x. But what's going to happen is when you substitute in a negative x, the only ones that will change are the ones with odd degrees. The others will remain the same. Let me go ahead and show you the substitution so you can see it and see what I'm talking about. So I'm going to go back to the original function, this big ugly one up here, and wherever there's an x, I'm going to put in negative x. Now keep in mind, this negative out here is going to have to stay here. Let me rewrite it with just parentheses first. So what I'm going to do is substitute in this negative x wherever I had an x and then clean it up. So when you raise a negative to an even power, it becomes positive. So this negative is just going to come on down. And when you raise a negative to an odd power, it becomes negative. So this is negative x to the fifth times 6, so that will change. This is also negative here. So when you raise a negative to an odd power, it becomes negative. Then you'll have a negative times a negative, which will become positive. 2 times negative x is negative 2x minus 2. So what happens if you compare this to the original? Notice the ones that had odd powers or the ones that had sign changes. This was an even power, sign did not change. This was an odd power, sign changed. This was an odd power, sign changed. This was an odd power because it's understood to be 1, sign changed. And of course you didn't substitute anything here, it didn't have an x, so it didn't change. So now let's look at our number of sign changes in h of negative x. Well, as we move along from the first to the second term, it's negative to negative. So there was not a sign change. No sign change there, negative to negative. And then from the second to the third one, it went negative to positive. 1 sign change. And then it went from positive back to negative, so there was another sign change. And then when you went from the fourth to the fifth term, it stayed negative to negative, so it did not change there. So that means in h of negative x, there were 2 sign changes. So that means there's 2, or 2 minus 0, which is 0, negative real zeros. That means 2, or 2 minus 2, which is 0, negative real zeros. Now this problem to begin with has 8 zeros because it's 8th degree. But if you notice, these don't add to 8. If you've got 4 positive ones, then that means there's 4 other zeros. So what are the other 4? Well, if there are even 2 negative ones, that still leaves 2 out. They're complex. Okay? So all your book asks for is the number of positives and the number of negatives. It doesn't ask for the complex. So what you need to do to find the number of positive real zeros is count the number of sign changes and decrease that number by 2 until you get to 0. Count the number of sign changes in h of negative x and decrease that by 2 until you get to 0. But what if the number of sign changes was odd? What if, let's say, f of x changed signs 5 times? I said subtract 2 each time. Okay, so that means there would be 5, or 5 minus 2, which is 3, or 3 minus 2, which is 1, positive real zeros. Subtract 2 from the number of sign changes till you get 1, or 0. So now on the previous page, we were subtracting 2 from an even number, so it went 4, 2, 0. But if your number of sign changes at odd, you still subtract 2, but you won't go down to 0. You'll go down to 1. Okay, there's some good examples of this on page 342 in your book, example 9. Okay, so your homework is going to deviate a little bit. So your homework, it's not what's on your assignment sheet. Your 4.4 homework will be 4, 6, 27, 28, 31, 36, 37, 44, 45, 51, 52, 55, 56, 82, 85, 86, and 90. So work on that. It's due at the next class meeting. You're responsible for it. Y'all have a good day.